In this video, I will present how ammonium, iron and manganese are being removed from groundwater in biological sand filters to produce drinking water. As explained in the previous video, these rapid sand filters receive anaerobic groundwater which has been aerated, for example with cascade aeration. The sand bed can be used for years or even decades without being replaced. You can imagine that on the sand grain surface in the filter, a biofilm will develop that can convert ammonium by utilizing the introduced oxygen in the water. During the startup of a new filter, it will take a few weeks for ammonium oxidizing bacteria to develop. But with time, the oxidizing capacity of the filter will increase. When tracking the nitrogen balance in the effluent of the filter, one will observe the following. Initially, all ammonium will pass the filter, but within weeks a fraction of ammonium will have been converted to nitrite. The presence of nitrite will onset the growth of nitrite oxidizing bacteria, resulting in complete nitrification. If we look at the nitrogen balance over the height of the filter bed, the ammonium will initially be removed over the complete height of the bed. But with time, the biofilm will concentrate in the top layer, resulting in a stratification of processes. In a steady state situation, ammonium will be oxidized to nitrite in the top layer, after which nitrite is converted to nitrate, deeper in the filter bed. Also, direct nitrification has been observed in filters, so in any case, in a good functioning filter, nitrate will be the only nitrogen species detected in the produced water. Where we know that ammonium oxidation is a biological process in filters, iron oxidation can occur both chemically and biologically. In anaerobic groundwater, iron occurs as ferrous iron, or iron 2+, which is a dissolved, reduced iron species. Chemical oxidation can occur in the water phase, as well as surface catalytic on the sand grain surface. Biological oxidation will only occur on the sand grain, as this is where the biofilm is hosted. While the rate of chemical iron oxidation to iron 3+ or ferric iron depends strongly on pH and oxygen concentration of the water. After aeration, oxygen concentration tends to be close to saturation, and the pH has increased due to the flush out of carbon dioxide. Therefore, iron oxidation will immediately onset in the supernatant water prior to filtration. The chemical reaction will result in the formation of ferric iron oxides, which are solid particles that will be trapped in the sand pores of the filter. Well, this is a traditional way of removing iron from groundwater. The past years, however, there has been increasing acknowledgement of the contribution of iron oxidizing bacteria, like Gallionella and Leptotrix, in sand filters. To select for the growth of iron oxidizers in biofilters, we need to slow down chemical oxidation by maintaining a lower pH, close to 7, and a lower oxygen concentration. By doing so, we avoid chemical iron oxidation in the supernatant, so the iron will enter the filter bed as the reduced iron 2+ species. The measurements in the slide show the iron concentrations prior and during filtration of a regular filter and a biofilter. It is clear that while particulate iron is detected in the regular filter, in the biological filter only dissolved iron is detected, meaning that all iron is removed on the sand grains. The biofilm on the sand grains will harbor iron oxidizers that can utilize this iron and form the most magnificent iron oxide structures. These DNA-shaped structures are found in the backwash water, but also accumulate in the iron coating that forms on the sand grains. This porous iron coating offers additional adsorption capacity for ferrous iron, further improving removal efficiencies. Well, when using oxygen levels that are only sufficient for the oxidation of iron, in the 1:4 molar ratio, all oxygen will be used by this process, and no ammonium oxidation will occur. In other words, under such conditions, we select for the growth of iron oxidizers at the expense of nitrifying bacteria. Manganese is a metal that is dissolved in anaerobic groundwater as manganese 2+. Unlike for iron 2+, chemical oxidation of manganese in the water phase is very slow and will not occur in the typical pH range in groundwater treatment. Manganese 2+ can oxidize chemically, however, when in contact with manganese oxides, forming new manganese 3 and manganese 4 oxides. This process is called autocatalytic oxidation and requires a manganese oxides coating on the sand grains in the biofilter. This sand, in new filters, will contain natural deposits of manganese oxides, as will be typically found, for example, in river sediments. These will act as a starting surface for development of a thick black manganese coating. While chemical manganese oxidation is the most established water treatment method, increasing scientific interest has also sparked the relevance of biological manganese oxidation. Manganese oxidizing bacteria form slightly different manganese oxides than chemically formed oxides, but detecting requires advanced equipment. We suspect that in the near future we will also be able to select for manganese oxidizing bacteria, which will further enhance the stable operation of groundwater biofilters. This brings me to some final reflections regarding groundwater biofilters. In a well-backwashed sand filter, the microbial community will be homogeneous over the height of the filter bed. During backwashing, sand grains will travel freely through the bed, exposing microbial communities equally to the different concentrations in the filter bed, also when stratification of processes has developed. As a consequence, various conversions in the filter bed may interfere with each other. For example, nitrification is known to be hindered by precipitating iron oxides. Also, the onset of manganese removal is known to be delayed by incomplete nitrification. Well, to avoid such undesired interactions, one could separate these processes into different sequential filters. In pre-filters, iron oxidation will dominate, whereas in the post-filter, ammonium and manganese removal occur. As a consequence, the pre-filter will contain orange iron oxide-coated sand, whereas the post-filter will contain black-colored manganese-coated sand. In practice, iron carryover from the pre-filter is observed, so the black coating will also contain impurities of iron. With two filters, a second aeration step can be added as well, which might be needed to supply sufficient oxygen and to reach sufficiently high pH for manganese removal in the post-filter. In groundwaters with relatively low concentrations of iron and ammonium, and thus lower oxygen demand, one could also design two compartments within the same filter. This can be done by applying a dual media bed, with a top layer of lighter material, like pumice or anthracite. The difference in density will prevent the sand and the top layer to mix, maintaining two distinct compartments for iron removal in the top and manganese in the bottom. It should be noted, though, that growth of the coating will change the density of the media, leading to mixing of layers over time. Also, the depth of the intersection between the two layers will have to be chosen smartly, namely after complete iron removal, but before the onset of manganese removal. Otherwise, coating growth will not be restricted to one layer of the filter bed, affecting the long-term performance. In conclusion, biological sand filters for ammonium, iron and manganese removal from groundwater harbor a wide range of biological and chemical conversions. By designing for the right process conditions, we can steer towards a specific conversion, allowing for more efficient filter operation.